So without further ado, let me introduce our first speaker. We are thrilled and honored to have Emma Strubell here. She is the Raj Reddy Assistant Professor in the Language Technologies Institute within the School of Computer Science at Carnegie Mellon University and a visiting scientist at the Allen Institute for Artificial Intelligence. They previously held research scientist roles at Google and Meta after earning their doctoral degree in 2019 from the University of Massachusetts Amherst. Strubell's research lies at the intersection of natural language processing and machine learning, with a focus on providing pragmatic solutions to practitioners who wish to gain insights from natural language text via computation and data-efficient AI. Their work has been recognized with a Madrona AI Impact Award and Best Paper Awards at ACL and EMNLP, and has been cited in news outlets including the New York Times and Wall Street Journal. Strubell has co-authored multiple papers on evaluating the energy demands of various uses and types of AI, and is part of an ongoing effort called the AI Energy Star Project, comparable to the well-known Energy Star ratings, which aims to prompt developers and users of AI models toward more transparency and consideration of energy consumption. Emma.
Yes, so thank you so much. I don't know where Irina went, but thank you so much for the fantastic introduction, and thank you so much for inviting me. Yeah, so I'm really excited to hopefully give a useful overview today about, the potential positive or negative environmental impacts of AI, and a little bit about maybe what we might be able to do about it. But I'm hoping I can just sort of start the conversation. So my background and expertise is more as an AI machine learning researcher and less as a, person who knows a lot about energy policy. So yeah, hopefully I can provide some insights from that direction. Okay, and so I'll start with a little bit about why we're here, hopefully, I don't have to convince anyone here. I think Irina already did a great job of this. That climate change due to humans is an incredibly urgent problem, specifically, I can tell you why I'm here, because the sort of impacts of what we're already seeing due to climate change are sort of in my face every day. For example, sort of one of the first, climate change impacts that really sort of hit me and impacted me was sort of noticing that the tide pools that I grew up, playing in and discovering creatures in as a kid have like changed substantially when I go back home now. The biodiversity is like obviously not there, and the mussels that we used to smash in order to like use as bait to catch crabs basically don't exist anymore. So not in my hometown, but in my current town, this is a picture of my street that I live on, which has collapsed due to a sinkhole. And I learned in some of our community meetings that for Appalachia, one of the things, and I mean, I think we've seen this also recently in North Carolina, for example, one of the manifestations of climate change is going to be increased flooding and sinkholes and landslides due to an increase in the frequency and severity of inclement weather events. And then even when I go on vacation, it's sort of in my face. So this is a picture that I took this summer hiking in the Alps, and just so the area of the southern French Alps that I was in was devastated by Storm Alex in 2020, completely, literally changing the landscape. So this is actually not, well, this is sort of like a beautiful mountain river, but this is someone's home that I assume is no longer sort of structurally sound, and this wasn't there a couple years ago. And literally the day before I arrived to stay at one of the huts in the Bourgogne, where I was sort of starting my hike, that the mountain hut had to accommodate tons of people who were evacuating because of a storm that had happened just that day and wiped out the bridges that were required. And the trail that I was hiking was completely rerouted. So I won't do the cheesy thing of asking you all to talk about or think about why you're here and how this is impacting you, but also, of course, it's impacting many people around the world, even more than it's impacting us. So this is a really urgent problem. And what can we do about it? So as I said, I'm a AI machine learning researcher, and I want to start on I want to maybe shift to a more positive and optimistic note, which is that I actually feel very optimistic and hopeful about how artificial intelligence, machine learning, can actually help us to tackle some of the problems that we're facing and that we need to resolve in order to sort of mitigate and adapt to climate change. So these are some figures from a fantastic report from the from CCAI, Climate Change AI, called Tackling Climate Change with Machine Learning. And on the left here, sorry, the right, you can see, you don't have to read all the words, but this is just a really long list of different potential areas where AI is and can be applied to potentially help with mitigation and adaptation to climate change. Along the top are just sort of different specific AI methodologies that can be used in those areas. And then on the left here, sort of a figure indicating sort of specifically how AI, I will talk a lot about how AI uses a lot of energy and that produces greenhouse gases. But AI models can also be applied in many cases to reduce greenhouse gas emissions, to solve the challenges that are limiting using renewable energy more broadly in our energy infrastructures by sort of better optimizing the energy grid. And yes, and I'll briefly talk about a couple applications, very briefly talk about a couple applications that I work on using large language models towards this end that I think are exciting. And so one is in discovering and decarbonizing materials. So this, I don't know the name of this type of chart, I can't remember it, but this chart is sort of demonstrating, well, essentially circular sort of pipelines involving greenhouse gas emissions of basically cement production, metal, specifically steel and aluminum production, and also petrochemicals, which, together, as you can see, make up maybe a quarter of global greenhouse gas emissions. This is primarily because the processes that are required to produce these things require emitting a lot of greenhouse gases and carbon, both because of the sort of chemical processes, but also just because a lot of fuel and potentially energy goes into those processes. And so an exciting area of AI applied to science that I work in collaboration with material scientists is sort of trying to better characterize and understand, how we could optimize these processes to make them actually more efficient and potentially discover new materials that will, sort of fit our needs, to, for example, replace cement or replace rare earth minerals in solar cells in order to make them less expensive, and automating that process and helping scientists in performing that research by using AI. So one of the things that language models are particularly great at, right, is synthesizing a ton of information from this huge corpus that a single human could never read. And I think that aligns really well with this this article discussing and sort of what have made some of the biggest the scientific discoveries that have corresponded to some of the biggest breakthroughs recently in materials science have all been when someone sort of realized that this process from this completely different literature could be applied to this thing where sort of no one had known about that process before. So it requires sort of synthesizing this information across many different literatures. Yes, and then so one of the other things that I work on too is so using language models to analyze climate, local climate action plans to assist policymakers in sort of analyzing and auditing sort of local climate-related policies. And I'm actually working with Tom Corringham, who's a fantastic research economist at University of Santa Barbara, I think. And we have this data set of climate action plans for municipalities in the state of California, actually. That's really fun and interesting to work on. Okay, but without further ado, of course, I'm excited about AI. I work on large language models, and unfortunately, that means that I am contributing to greenhouse gas emissions, which are the primary source of climate change. Yes, and so this is definitely a problem. We've seen, many of you probably have seen these But one of the things that we're seeing this year is pretty strong evidence that basically the increase in energy use in data centers powering artificial AI, and specifically, these advances in generative AI and newer AI technologies, is actually leading to basically having to use more fossil fuels and reducing the speed at which, at least in the US, we're able to retire our fossil fuel energy sources. So this is a chart and a quote from a recent Wall Street Journal article about this. So what this chart is showing is sort of projections over time on the reduction in coal burning power plants in the US. And so you can see that basically compared to the 2023 expectations, sort of after the year 2022 to 2023, they've sort of adjusted those downwards because after many years, potentially sort of decades or maybe 15 years of sort of flat energy use in the United States, it's sort of drastically increasing. And so we're not going to be able to retire sort of fossil fuel energy production as quickly as we had hoped. So this is another chart of something sort of similar that's basically demonstrating. So when you have sort of peak energy demand, sometimes you have to turn on less clean burning fuel production that can sort of be turned on and off on demand easily. So this tends to be fossil fuel powered. And so this chart is showing how many of these sort of extensions had to happen, and they almost doubled between 2021 and 2022, which is much higher than previously. So this is leading to more greenhouse gas emissions due to energy use. And sources are attributing this to the increased energy demand of artificial intelligence workloads running in data centers, alongside manufacturing and the broader electrification effort, right? There's more of us charging our electric vehicles at peak times, and that's also causing more greenhouse gas emissions, unfortunately. And you'll notice this is a correlation, not a causation, but this is right when ChatGPT was released at the very end, I think early December 2021, which sort of corresponds to this recent boom in generative AI. So we're seeing these significant increases in energy use, leading to higher dependence on fossil fuels. And the leading companies that are responsible for developing these exciting AI models are reporting that they're struggling to meet their own goals for net zero emissions as a result. So right now they all sort of voluntarily report, produce these environmental sustainability reports every year. And since 2020 or so, many of the leading tech companies have stated that they have these goals to be net zero carbon emissions or net negative carbon emissions by 2030. But unfortunately, in their reports for this past year, 2023, which were released this year in 2024, almost all, many of these companies are reporting that, in fact, their greenhouse gas emissions have been increasing year over year. So these are some examples of news articles discussing Google's report specifically, where their carbon emissions, greenhouse gas emissions, have actually grown by about almost 50% since 2019. This is equivalent to about 38 gas-fired power plants, the emissions that they would release annually. That's pretty significant. It's not just Google. So I didn't actually get a chance to go through, I have a list of these ESGs. They're really fun to read. I didn't go through all of them, but I almost guarantee you that all of them will have sort of the same results. So Baidu's specifically says that rapid development of large language models is posing severe challenges to their development of green data centers. And despite significant efforts towards transitioning to significantly more renewable energy over the past year or the past few years, they also report a 30% increase in greenhouse gas emissions over a 2021 baseline. And then Microsoft reports also greenhouse gas emissions up 30% over a 2020 baseline as they continue to invest in the infrastructure needed to advance new technologies. Okay. So so AI definitely is contributing to climate change, at least due to the greenhouse gas emissions from the really high electricity energy demands. So that was my point, that like I'm only citing these two. I haven't had time to go through all of them, but like it's in a lot of them. It's not specific to those companies. So hopefully now I've established that the relationship between AI and climate change and AI and the environment is somewhat complex. So how do we characterize the role of AI in relation to climate change mitigation? So this is a figure that we developed in an article on this. It was published a few years ago, where we sort of tried to sort of outline this. So in the center here, so we sort of divide the environmental impacts, positive or negative, into these three sort of categories. At the inner circle, we have the compute-related impacts, and I'll talk about like all of these things in a bit more detail in the talk, but to give like a high-level view. And so these are the environmental impacts that sort of I've just been talking about. So this is like the greenhouse gas emissions due to developing models, also potentially due to manufacturing of the hardware that's needed to sort of run and develop these models. In this second sort of circle, we have the immediate application impacts. And so this starts to highlight something that is really important, which is that the actual applications that AI is being developed and used for is going to make a big difference in terms of like what is the actual environmental impact of AI. Some examples here are, AI could be used to, for smart buildings to allow them to use their HVAC systems sort of more efficiently and reducing emissions. AI can also be used to, potentially search for, better places to drill for oil and facilitate more oil drilling. The way that we've organized this chart is actually, as you go further from the center, basically, I think the potential impacts, positive or negative, actually get much larger. But unfortunately, the complexity of trying to sort of model and characterize those impacts also becomes larger. So it gets much harder to sort of understand and characterize the impact. And then in this sort of outermost region, so this corresponds to system level impacts. So this includes like rebound effects and things like this. So as the economy sort of digitizes and as new AI capabilities sort of change what society looks like, what work looks like, how we function, that is going to lead to these sort of systemic changes that also potentially could have the most significant changes in terms of AI's impact, positive or negative, on the environment. So an example of this might be, self-driving car technology, which could lead to, more people taking self-driving Ubers potentially, which would maybe not be the best thing for the environment. It could also lead to, sort of better public transportation infrastructure, which could lead to, positive impacts or like mitigation or reduction of bad environmental impacts. Yes, okay. And so I said this, the emissions impact depends on the application. These are just some examples of like specific sort of machine learning technologies on the left, and potential applications that each of those technologies could be used for on the right. The red ones are examples of applications with potentially negative impacts. The green ones are examples of applications with potentially positive impacts. And one thing that I want to highlight is like the dual use issue, right? Because you'll note that each of the sort of methodologies or modeling frameworks on the left corresponds to both good and bad impacts, potential, and task uses on the right. Okay, so, limiting global warming to non-catastrophic levels is going to require sort of rapid, far-reaching transitions in energy, just like across all of our sectors, collaboration and understanding. So yeah, AI can potentially help with that. According to some specific scenarios for sort of net zero emissions by 2050, we need to reduce specifically emissions, greenhouse gas emissions due to data centers by half by 2030. And if you recall my citations, we're moving the opposite direction, unfortunately, right now, probably due to generative AI and the increased use of AI and the energy demands that has. But we know that artificial intelligence has great potential for either positive and negative impacts. So I think what we're here today to try to start figuring out is how we can shape a future where the positive impacts outweigh the negative ones. That's not going to be easy. Okay, how am I on time? What time do we end? Okay. My talk is probably too long, but that's okay. I'll try to adjust. It's a chronic issue I have. Okay. Okay, so outline for the rest of the talk. So first I'm gonna sort of talk in a little bit more detail about what we do know. So what we do know about sort of some specific facts and figures about where the greenhouse gas or general environmental impacts of AI come from, mostly the negative ones. I'll spend sort of the most time on that because it's the area that I know the most about, and also the area that that I have the most information about. Then I'll spend a little bit of time talking about what we don't know. So what are some of the remaining knowledge gaps and sources of uncertainty in terms of doing those characterizations and understanding that relationship. And then I'll say a little bit about sort of what next, although that's sort of my that's where I know the least, and so I'm hoping that'll be a stepping off point for discussions for today. Okay, so now I want to give a little bit more concrete of a characterization of how AI impacts the environment. And so one of the areas that you're probably most familiar with and that I've spent the most time talking about so far is the operational impacts of AI. And so these are the impacts that correspond to the development and use of AI models themselves. AI also has embodied environmental impacts, and so that corresponds more to the hardware manufacturing, cement production required to make the huge data centers, building infrastructure, and then the disposal of that hardware that goes into building AI. And then, of course, I've mentioned this. There's also these downstream impacts, which can be potentially positive or negative, which is how the AI models are actually applied. And so what are the more sort of specific mechanisms for what are these impacts, where do they come from? So I'll list some here and also give some examples. So, of course, greenhouse gas emissions. Water withdrawal and consumption is also another sort of emerging concern. Deforestation as well. I'll speak less about that today because I know less about it. I think everyone sort of knows less about it, but also an emerging concern. And then these sort of more complex systemic rebound effects, which I'll talk a little bit about. So some examples, of course, fossil fuel-based data center energy is an example of where greenhouse gas emissions come from. That's an operational impact. Greenhouse gas emissions also come from the hardware manufacturing process, both from the sort of chemical processes that happen to sort of forge the chips, or sort of in the foundries to make chips, but also because energy use is required in that stage as well. Water withdrawal and consumption, it also just comes from energy, right? So nuclear power plants evaporate water in order to cool things. Data centers also most frequently use evaporative cooling, water-based cooling systems to cool the sort of very intensive hardware that produces a lot of heat energy. Deforestation and sort of biodiversity reduction comes from the mineral extraction. So the hardware requires a bunch of specialized minerals in order to work well and conduct things. So that is also a problem. And I think I also listed, there's a lot of different examples that I have not listed here, but I wanted to give a few. So I'll start by talking about the greenhouse gas emissions because it's the area I know the most about, and also the area that we all, everyone, the field kind of knows the most about. Yeah, okay. So, so for folks who do not come from an AI machine learning background, I want to spend a slide sort of talking about like why recent AI models use so much energy and why we're sort of not really able to do that much about it. And so the issue is that the current best methodology for improving AI capabilities and that gives us like these really cool new exciting capabilities is to train these models on sort of as much data as possible. And so the way that we do this is by increasing the size of the models, like the number of parameters. They're literally like statistical models with tons of parameters. Roughly, so increasing that size of parameters roughly in proportion with the amount of available data. And so this just directly corresponds to increased computation, literally multiplications and additions, basically. And that increased computation requires corresponding energy to power the hardware that does all of these, bajillions of computations. So this is a little bit more detail than you need probably, but this is just a plot from the OpenAI's sort of GPT-3 paper, basically sort of demonstrating, so the 3 different lines correspond to different sizes of models and sort of therefore sort of different computational efficiencies or computational workloads, with the blue one being the highest. On the x-axis is sort of not that important. On the y-axis is like the sort of accuracy of the model or the sort of capability level of that model. And so you can clearly see that the larger, more computationally inefficient model, the blue line at the top, is like sort of doing much better than the other 2 smaller models. So this is sort of a similar plot, a similar set of plots. So for a bunch of different capabilities or tasks that people think are sort of interesting for these models to have, on the x-axis is the sort of model scale. So it's the amount of sort of computation basically required to produce the model. And on the y-axis, again, is sort of accuracy. And so what you can see is that there's this point where its model sort of has to be large enough for these different tasks to see those capabilities and those performances come out. It is possible that there's a lot of, well, I'll talk about this later. That's the current state of the art, though, and that's sort of the problem. We don't have good ways of significantly reducing the amount of energy, in a game-changing sort of way while maintaining the capabilities that we want and need. Okay, so from the top down, how much energy is this actually using? So this is another figure from that Nature Climate Change paper from a couple years ago. So of global greenhouse gas emissions, at least as of a couple of years ago, the amount of global greenhouse gas emissions from basically computing and information and data transfer, ICT sector, is about 1.4 or 1.5% of global greenhouse gas emissions. So that's the maximum sort of regime that we're working with right now. That is going to increase over time, as we digitize the economy, of course. So of that, a subset is sort of AI related. At the time we made this chart, we sort of had no idea how much that was. More recent reports now say it's about 10 to 30% of data center workloads are AI related. So about 10 to 30% of that is AI. So some more specific statistics. So AI workloads, according to Google, made 10 to 15% of their total energy consumption as a company between 2019 and 2021, which corresponded to 1.5 to 2 terawatt hours of energy in 2020. And as you may know, Microsoft in September signed a deal to reopen the 3 Mile Island nuclear power plant and purchase all of the energy produced by the remaining safe reactor for the next 20 years, which will be equivalent to powering about 800,000 homes per year for the next 20 years. And they're going to be using that to power data centers. Okay. So going a little bit deeper, where does this come from? So machine learning models need to be sort of developed and trained, and then they also are used. And so the thing that I want to point out here is a lot of focus is on the really large energy consumption due to required to train the models and develop the models, but that happens very infrequently. But it's sort of easier to measure. use happens much more frequently, right? Like how often are all of us / everyone in the world just like doing a Google search and getting like the AI Gemini summary at the top? Each of those corresponds to a use. So each use or inference requires sort of significantly less energy than training and development. So this is an example for a small-ish large language model where the energy use in terms of number of inferences or uses or queries that corresponds to the amount of energy required to train the model is about almost 600 million inferences to equal a single training. But at large companies, like that is sort of easily happening per day, right? Yeah, and so the key idea here, I don't know if I need to go into detail about this, but yeah, is that there's a lot of focus on training because this is one big use, but I think the data sort of shows us that in fact we need to focus more on inference. So this is a breakdown I probably won't go into from Meta, just about, so the relevant thing here is that we have very little information actually that at this level. So most of the data and information we have access to is at the sort of data center level. We sort of know how much energy data centers are using. We do not know exactly sort of which workloads that corresponds to. We have little bits and pieces sort of published by companies, sort of stale data here and there. This is an example from Meta, who's one of the best companies about reporting these things. They report that of all the energy use due to AI and machine learning, this was as of, I don't know, 2020 maybe, it was about 70% inference and 30% training, and Google reports like a similar number around the similar time frame. So it's about 60-70% of energy at Google and Meta being used for AI is being used for inference, so for the use by users rather than the training. So bottom up, like I said, this is like the easiest thing we can quantify is sort of like how much energy is required to do training or inference of like sort of a specific model. So this is from a study that we did with Microsoft a few years ago for a bunch of different, measuring the CO2 equivalent greenhouse gas emissions of a bunch of different models that they actually trained, in their actual data centers with the actual sort of carbon intensity of those data sources. And so training what is now basically like a small, sort of almost useless, not useless, but a small language model, much smaller than like what OpenAI is using, required to train it 13% of the way, because we didn't rerun any of this stuff. We just used the data that was available. We only had like the 13% of the training available. Use the amount of energy approximately equivalent to powering a average US home for a year. That was only 13%, though, so it's actually higher. We have some more recent numbers as well. So Meta's popular open source Llama 3 family of models, they report used about 11,000 tons of CO2 equivalent emissions. This is similar to about, for like average electricity intensity in the US, almost 1,500 US homes, or 2,700 sort of like more, combustion engine vehicles on the road for 1 year. Google reported for their open source models, it was like an order of magnitude smaller, so about 1,000 or 1,200 tons of CO2 emissions. But notably, these are like their sort of open source models. These are not their actual production models, and they do not report any numbers like this for those models. So that was all the sort of training and development side. You can also look at how much it costs to do these uses. So for example, generating an image or for ChatGPT to generate a response. So sort of at a high level, what does this look like? I think one of the key takeaways is that there's like huge variance depending on the model and the task. One of the things that we found is generating an image is much more computationally expensive than generating text. So maybe think twice when you're sort of generating silly images to use in your PowerPoint slides. Sort of one of the most efficient models that we used approximately 0.1 watt hours to process 1,000 questions, question answering model. So it's about similar to the energy needed to power a 25 watt incandescent light bulb for 5 minutes. It's for answering 1,000 questions. And the most expensive model that we experimented with required about 1,600 watt hours to generate 1,000 high definition images. That's similar to the energy needed to fully charge your smartphone about 70 times. These are basically certainly high estimates because the systems that we're evaluating here are not as highly optimized as the ones that would actually be running in deployment at tech companies. So take that caveat with a grain of salt. But the relative amounts are still the same. Yeah, okay. So I think I'll skip this a little bit for time, but these are just some sort of takeaways. I think maybe a key takeaway of interest here is that I think there's a lot of push to use, these newer sort of more general purpose AI models as a sort of like one size fits all solution, because that's what they do. And that's kind of what's cool about them, these general purpose models that can kind of do anything. But in terms of energy use, it is much more efficient if you have available or can create a task-specific model. If you have like a specific task you need to do, you should have a specialized model to do that task. It's going to require much less energy than sort of using the really big model that's essentially like probably overkill because it can do every task, sort of, to do your one specific task. Okay, so what are some of the current sort of like mitigations to these emissions due to energy use? And then what are some sort of challenges that correspond to those mitigations? Why is this not solved? Okay, so one mitigation, of course, just as in other sectors, is just transitioning the energy sources that are powering data centers and hardware manufacturing to carbon-free energy. And this is exactly why you see multiple tech companies sort of investing now in nuclear energy, because it's carbon-free. So some challenges, basically need 24/7 energy supplied to data centers, and we don't have the sort of like battery technology, basically, to support that for renewables. Yeah, so we just generally need sort of significant investments in the energy grid in order to support like the amount of renewable energy that would be needed, and trying to provide it in a 24/7 way. Yes, and so one of the main things that companies are turning to now is, they're sort of buying old nuclear reactors, but they're also interested in investing in and building these small modular reactors. So it's like a newer, safer, smaller nuclear reactor technology. I did some research on this. To me, it seems like it is unclear. So there's basically like conflicting reports and studies. Some say that these small modular reactors actually produce more nuclear waste per sort of like kilowatt hour or kilowatt produced, and like worse nuclear waste than like the larger reactors. There's another study that says that this sort of like isn't the case, and so it seems like that is like a current area of scientific debate. But that may be of concern. Yes, so a lot of people are saying basically this is not a problem because we'll have efficiency gains in AI hardware, software, and algorithms. It's just like a really bad argument. Sorry, I'm a little bitter because there's like, yeah, some tech executives who like disagree with me on this. So far it's not working. Like so far we have not made efficiency gains. Despite significant efficiency gains across all of these, it is not enough to keep up with increased demand, and we see that because all of these companies are working very hard to implement efficiency gains and reduce the energy use, right? Even just from a cost like perspective, and yet we're seeing their greenhouse gas emissions like increasing year over year. So I don't think it's impossible, but a significant methodological paradigm shift is going to be required on the hardware side and or on the algorithmic side, and so we don't know if that's going to happen. I'll talk a little bit, hopefully if I have time, about rebound effects as well. But the issue here is sort of like the curse of efficiency or Jevons paradox, right? Where if you actually do improve the efficiency or reduce the amount of energy required for these processes, they're going to be used more. It sort of like allows you to deploy them in more spaces, more affordable in more places. That can actually lead to more energy use or more use due to the efficiency gains. That's why it's a paradox. And the primary current solution to this problem and the way in which these tech companies are achieving any amount of sort of like carbon neutrality currently is through carbon offsets, power purchase agreements, and renewable energy credits. So this is when you emit some kind of greenhouse gas, but then you purchase renewable energy somewhere else, or invest in carbon capture projects, planting trees, things like this, such that the carbon reduction or mitigation is equal to the carbon emissions. So there's a ton of challenges in terms of the actual efficacy of these methods. One is that it's just very fundamentally challenging for the actual geographic location of the emissions to sort of do a good job of corresponding to the mitigations, the offsets. And it's also just very difficult to verify that. Are you coming to tell me I need to really wrap up? Oh, okay. Okay. Well, we can talk more about other things that I'll miss. Yes. So verifying additionality. So this is basically validating that the reduction in carbon wouldn't have happened anyway. So sort of if you're buying this renewable energy, would someone else have bought it anyway? In which case, it's actually not additional to the sort of net emissions. 5 minutes. Okay. What do I cover? Good. Okay. I already mentioned rebound effects a little bit. So the curse of efficiency. Yeah. So this is that idea that actually improving efficiency can actually lead to overall higher use of the resource because it increases sort of access. Okay. Then I was going to talk about water withdrawal and consumption, but I may sort of just skip it. We have someone who's more of an expert on this than me here, anyway, Chalet, so he'll probably talk about this later. We can hear about that. But AI models use water. I was going to talk about how and where they use them. It's probably a problem, yeah. I will highlight maybe some of the mitigations and challenges to this. You trust me that it's an issue? Okay, we have a whole panel on that. Yeah, I won't. Okay, that's coming next. You'll hear more about it from people who know more about it than I do. Okay, good, perfect. Okay, so this is a slide I actually really want to talk about, which is the sort of what don't we know? Okay, so this is a chart of a bunch of different projections for how much, for basically projected data center energy use in the US over, until sort of 2030 from a bunch of different think tanks, I guess, whoever makes these projections. And so the thing I want to highlight from this is that there's a difference of about almost 500 terawatt hours per year across these projections, which is greater than 10% of the US total energy use, that we used in 2022. So basically we cannot make these projections. We're really bad at it. And so that's a problem because it's really hard to actually design policy and stuff, right? If we have sort of no idea what's going on. Why is this happening? In my opinion, it's because there's huge knowledge gaps in measurement. So overall data center energy use, I mentioned this earlier, is an insufficient metric. We need more detail on what is actually driving that energy use in order to develop more fine-grained, detailed, and accurate models for projecting how energy use is going to proceed. So what proportion, examples of questions we don't know the answers to. What proportion is AI or generative AI? How much is AI development versus use? What are the specific use cases and applications, right? This is going to be really important for trying to figure out these trade-offs between what is the technology actually being used for and developed for, and how are the sort of investments in that corresponding to the actual changes on the ground. Yes, and yeah, in particular, I want to highlight that most data focuses on the training and development aspect and not the use or inference aspect. And this is in part because we rely on the companies that are developing and deploying these technologies to report the statistics about use, but they don't. So this is an old example from a 2018 paper from Meta that does give us sort of some information about that, but it's just extremely rare, few and far between, and not enough to make projections based off of. Okay, I could go to questions. You want me to go to questions now? Basically, very quickly, I think we need mandated reporting. So right now, most reporting is sort of because the tech companies are willing to do it and they want us to perceive them well. I'll highlight, there are a few changes to this going into effect soon, including in California, which is amazing. So EU data center operators will have to report yearly water and energy consumption starting maybe this year or next year. California Senate Bill 253 is fantastic and will require yearly corporate ESGs for any businesses operating in the state, which my understanding is like actually applies to anyone with users or consumers in the state, beginning in 2026. So these ESGs, those are these like sustainability reports that I like to sift through where all this data is available. And then Germany's Energy Efficiency Act actually sets targets for data center efficiency and renewable energy, which is like fantastic. We don't have anything like that in the US. And in fact, it's sort of the opposite last week, where it was like, we'll develop AI infrastructure, or yeah, energy infrastructure to support AI as sort of at any cost as a defense issue. Yes, okay, so this is Energy Scores Project. I'll talk about this briefly and then I'll finish. Yeah, so one thing that we're doing towards this to try to facilitate this communication across like policymakers and sort of like people who aren't necessarily AI experts, to sort of understand this and empower people to make better decisions about energy use of their models, is this AI Energy Score project. The EPA contacted us and let us know that Energy Star is under trademark and we cannot call it Energy Star anymore. So inspired by the Energy Star project of the EPA, Energy Scores. And so basically, yeah, we're measuring the energy requirements and greenhouse gas emissions of as many AI models as possible. Right now, it's basically open source AI models. We did it ourselves for the most popular, the most downloaded ones, but you can also just submit your own and run the analysis on Hugging Face's GPUs, which is fantastic. And we're working on getting buy-in from companies to also, we have like an evaluation harness that they can download, evaluate their proprietary models, and then submit the results for us to include in sort of like a proprietary model leaderboard as well. So for folks who don't want to open source their models. Okay, so I'll skip this, which is another thing that we've done, and hopefully have some time to take some questions, but I'll be here all day so we can chat as well. Thank you.
A couple of quick questions for now. One is, first of all, I just wanted to point out that even some of the numbers you gave were from like 2020, and that's before the launch of ChatGPT, right? So when we talk about cost of inference versus the cost of inference, now that we have AI summaries in Google search and all these other models from Microsoft, OpenAI, Meta, Amazon, Baidu, think of all the others I'm not naming. Those numbers are essentially no longer very useful, right?
Yeah, I mean, certainly higher. Like they have only added computation. But yeah, we can kind of estimate, but we don't exactly know what that looks like because it's not reported. Yeah.
Do you have a sense of what environmental impacts are most felt in the communities where data centers are located?
I think probably the water impacts. That would be my guess. Yeah.
and we're going to talk about that more in the water
panel.
I can talk
more
justice.
About that. But there's both with water withdrawal and water consumption. And I think even water withdrawal, right, corresponding to, again, at least tens, if not hundreds of thousands of homes, in a place with maybe a data center, but in particular in this case, like a hardware manufacturing plant. It takes a toll on the water systems, both like the human water systems and the environmental water systems in a significant way.
So in terms of one question I have is, I've been recently in meetings in which people who apparently even advise governments are saying that the training cost is the main energy use, that inference is small. And at the same time reading things that say inference is now accounting for 70 to 80% of the energy cost is what I've been reading. How do we get that information to the people who are supposed to be educating everybody else? How do we, given the challenge that we don't even have information, but we have some, and at least more accurate estimates, how do we make sure that we can get that information out there quickly enough to impact policy?
I don't know how to do this in a systemic way. That's like why I'm here. And I also, I serve on, panels with like government, like I recently was on one with like the GAO, Government Accountability Office, who was developing like a report on this. I'm contributing to like another report discussing like the environmental impacts of AI. So that's what I'm doing. Like I'm trying to stay involved in those things. Although I will say that the incentives for like AI ML people to be involved in that stuff are like not great. I don't know. I don't necessarily get credit for it. Yeah.
What
like
would make for better incentives?
Yeah. I don't know if I have an answer to that.
That's
happy to discuss further though.
Yeah, and I think that's a good question for all of us to keep in mind then.
Exactly. No, I think this is a huge issue. Like we really, as I said in the beginning of the talk, we need more interdisciplinary collaboration, both between sort of policy people and people sort of like on the ground in the different sort of application areas where policy is relevant, but then also just like within the sciences, like across fields and things. And it's really hard, I think, in our current systems, even just like getting funding from the NSF. I don't know. I've been waiting for weeks to hear back about like where I should send this grant that's sort of interdisciplinary. And they're like but they really want you to do interdisciplinary research, and it's sort of like not working. So I have complaints, but no solutions on that right now. But this is why I'm here. I want to discuss these things. Yeah.
Thank you. Let's see. Are you started out by talking about your optimistic view, right? So one of the questions from the audience is, are you ultimately optimistic or pessimistic about the ability to reduce carbon emissions from data centers before 2030?
Oh, before 2030, I'm very pessimistic. Sorry. Yeah. I think I'm more optimistic about initiatives. I mean, California is fantastic, and does drive policy in the United States, as we know. So maybe that's a reason to be optimistic. I think, like we saw the EU and Germany, I think cares a lot about this. I'm traveling a lot. It's not good for the environment, but next week I'm going to be in Germany, sort of giving some version of this talk to their Ministry of the Environment and Nuclear Energy and stuff like this. So they like care about this. So I'm hopeful that maybe other parts of the globe can be leaders in this. Yeah. I think it's part of the U.S.
You mentioned very briefly just at the end of your talk that the U.S. government is now actually pushing for the building of infrastructure for development and usage of AI. So any suggestions well, first of all, do you have a sense whether the environmental impact is being considered as part of those conversations? Because it sometimes seems to be left out entirely.
Yeah.
And if so, do you think that there's some balancing coming up between, okay, we need to build versus we need to build carefully?
Yeah, I think that's going to be a really important concern. I don't see a lot of discussion in those conversations or in those, executive orders, or I don't remember exactly what this note was from the president's office. In that case, they were sort of discussing, the national security concern. And I think, usually what the trend is that, well, of concern for national security, like probably the environmental impacts take, go to the back burner or something like this. And, we also saw this sort of similarly in like the CHIPS Act, which sort of had similar motivations, right? We need more chips manufacturing to be happening in the US. There was basically no discussion, right? That could have been an opportunity to say, we need chips manufacturing and let's use this, to build new facilities and make sure that they meet like fantastic water use, energy use standards. We're powering them with like renewable energy or other like carbon-free energy sources. That was not in there at all. And I'm sure this was needed because it was like to pass something in the United States, it was bipartisan. But I think there's missed opportunities and we could do better.
And last question, I think just yesterday, Meta announced that they're working on a much, much bigger model. And, Elon Musk has talked about his much, much bigger Grok model.
That's what a waste, yeah.
So far, the trend seems to be, you talked about more targeted, smaller models that work well for a particular task. Is your sense that so far the push in industry is still for bigger and bigger general models, even as we're seeing all of these effects?
Definitely, yeah, because it is it's sort of like an arms race, unfortunately, right, between the different companies. And so like the easiest, there's a lot of pressure, to produce better models quickly and faster than the competitor. And the fastest way to do that is sort of ignoring efficiency, energy concerns, just throwing a ton of computation and a ton of energy and a ton of carbon at it. I do think, I think there are startups which by necessity, like they don't have the resources to do that. And so they're going to need to innovate in sort of like smarter, more clever ways, because there is, I could give a whole other talk about this, but I'm very excited. And one of the things that I am working on is, how we can, sort of take the capabilities of these large models, distill them into sort of smaller task-specific models. First, I'm trying to actually characterize like sort of what the pathways would look like for that in terms of that could lead to higher or lower energy use, right? You're sort of generating more models. But I think there are possibilities for this. It's not necessarily what's happening at the sort of biggest tech companies, but I think like sort of smaller startups are sort of trying to figure this out because they have to.
Right. Well, I think we're going to end on that note. Please join me in thanking.
Thank you so much,
Professor Strubell.